Alright, so we're going to start, like I said, with inverses. So, what do you guys remember about inverse functions from pre-calculus? Want to give me just anything you remember about them? One divided by it? That's actually a reciprocal. But they're often confused, inverses and reciprocals. So, think about the graph of a function and its inverse. What should be going on there? Anybody remember that? How? Opposite. Not necessarily. Sometimes they are. Yep.
When you switch y and x.
Yes. Yes. So it's an inverse basically is when x and y switch roles. Okay. I think a lot of you guys are getting it confused with reciprocals and making things negative and that sort of thing. It's not that. It's x and y are swapping roles. So we're going to look at this in two ways. One, algebraically, so just looking at an equation. And then number two, graphically. So what happens in the graph then if you switch those two things up? Okay? So let's start with the algebra. So if I had some kind of an equation, y equals x squared plus 2. Okay? And let's identify for a second the domain and the range of this thing. And then we'll work on the algebra of getting the inverse of this. Okay? So, what is the domain of x squared plus 2? Mm-hmm. And what's the range? 2 to infinity. Good. Okay, so what's the inverse then? So if x and y are going to swap roles algebraically, what does that mean? What are we going to do to the equation? Good. Yep. X equals y squared plus 2. Okay. And what do you suppose the domain and the range are? They are switched. Exactly. If x becomes y and y becomes x, then those numbers for which we can use x become those numbers for which we can use with y. And those numbers for which we can use with y become those numbers we can use with x. Okay? So our domain now is 2 to infinity. And the range is negative infinity to infinity. Okay? That's an important thing to remember with these two. That's a helpful fact. Okay. Now, one thing you're going to be asked to do with inverses is once you have the inverse relation, okay, we call it a relation because it's not necessarily a function yet. Okay? But one thing you might be asked to do is determine is the inverse a function or not, and if it is, write a formula for it. Okay? So how do we check to see if this thing is actually a function? What was the process? Yeah, you're trying to get y equals. And remember, a function has one output for every one input. So when we do that, when we solve it for y, that's what we're going to look for. It's the easiest way to check, is after it's solved for y, are we getting just one output for every one input? Okay? So we'll quickly go through the algebra of converting that then into a y equals equation. So x equals y squared plus 2. So this is us checking for a function. All right, so x minus 2 equals y squared, and then if I swap it around, I'm going to have plus or minus the square root of x minus 2. Because remember, negative or positive, if you square it, it becomes positive. So if you're using a square root to undo a square, you have to consider both the plus and the minus there. So it's plus or minus the square root of x minus 2. Is that a function? Am I getting one output for every one input? No. I'm getting 2, right? Every time I plug a number in for x, with the exception of the number 2, because then I get 0. But if I plug in like a 3, 4, 5, what have you, I get 2 answers every time. So this is not a function, okay? And we're going to take a look at the graph of this as well, and that'll be apparent on the graph when we do that part too, okay? But this is, yeah, not a function. And the big red flag for that is this plus or minus thing, okay? If you have a plus or minus, not a function. Okay, so that's doing the algebra part of it. So graphically, what do we have here? So if we think about our 12 basic functions and transformations, we can graph x squared plus 2 without too much difficulty. A little bigger. Okay. So, how do I graph that though? What's it look like? X squared plus 2. It's not to the right. It's not to the left. It's up. Okay, so remember, transformations, if it's a plus or minus on the outside, that's up and down. If it's inside, so if it was like x plus 2 in parentheses squared, that's going to be a movement like to the left too. And if it was a minus, it'd be to the right too. Okay, so we'll go back and revisit some of those things later. But for now, we're just going to run with it here. So, all right, so that's kind of what it looks like. This is at 2. Okay. So does anybody remember on a graph what happens when we graph both a function and its inverse? It kind of looks like a rotation. It's not actually a rotation though. Can anybody help her out? What's actually going on there? It's not a rotation, but it's a what? It's a reflection, okay? And it's a reflection over a diagonal line, so it looks like it's a rotation then, but it's this x equals y line. Yeah, it just comes right up like this. Okay, so think about that though. That should make a little bit of sense, because if x becomes y and y becomes x, okay, suddenly like this point right here, which is 0, 2, becomes 2, 0. So it starts actually over here at 2, okay? And all those other little ordered pairs, all their x's and y's are swapping, 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 swapping. And that reflects it over that line and pulls it over here, okay? So it looks like this. Okay, maybe not drawn to scale the best there, but you get the idea, okay? So this curve up here, this is the y equals x squared plus 2, and this is the x equals y squared plus 2. Okay? And using algebra, we were able to verify that that inverse was not a function. Look at the graph of the inverse. How can we tell from the graph that it's not a function? Vertical line test, exactly. Vertical line test says if I can drop a vertical line through a relation and I can find a place where it hits more than once, then it's not a function because I've got more than one output for one input. So for example, if I were to put a vertical line through it, I get 1, 2 places that it's hitting right there. Okay? So here's a question for you then. Without graphing the inverse, without doing the algebra to determine if it's a function or not, how could I just look at the original graph and tell if the inverse is going to be a function or not? Horizontal line test. Right. You guys remember that from pre-calc? Okay. So if the inverse is going to have a vertical line test determining if it's a function, the original function should have a horizontal line test that could tell us the same information. Okay? Because x and y have been switched, so I could have gone into my original function and said, I know right away, that's not going to be, the inverse is not going to be a function because I got this horizontal line that I can hit more than once there. Okay? So functions that do pass the horizontal line test have a special name. They're called one-to-one, which means one input for every one output, but also one output for every one input. It goes both ways. Okay? So for it to be invertible, that's got to be the case, right? It's got to be able to have that work both ways, because as soon as x and y swap, then it's going to have to work the other way too. Okay? So let's define that here real quick. Okay, so the formal definition of this is f of x is one-to-one on a domain D if, sorry. That's better. Okay, so f of x is one-to-one on a domain D if f of a is not equal to f of b whenever a is not equal to b. All right, now that's kind of just a functional way of stating the same thing that we just talked about, though. Okay, so I can't have two places on the function having the same y value anywhere, is really what that's saying. If I pick two different x's, I can't get the same y, okay, passing the horizontal line test. So I'm just going to put in parentheses here because this is really what you're going to look to determine it. It passes the horizontal line test. Okay, so you're gonna so part of your homework, you're gonna have a bunch of graphs to look at, and it's gonna ask you, or it might ask in a couple different ways. It could ask you which of the functions are one-to-one, or it'll ask which of these functions have an inverse that is a function. Okay, but that's asking the same question then. Okay, so that's all that type of stuff. So I leave you guys to investigate that a little bit later, because we're going to move on here. Okay, so let's get into some logarithms next then. All right, so just a little review again. Like I said, there's some logs that we've looked at in the past. But before we can get into what those are, let's define log real quick, because there's some restrictions we have on how or what numbers we can use when we're working with a log. So logarithms always come in this kind of variety, a log base a of x. Like I said, there's some restrictions on it as far as what the base is that you can use, and this all stems from what numbers we're allowed to use in exponentials, because a log comes from an exponential, which we'll discuss more in a minute. But basically, be greater than 0, and a can't be equal to 1. Okay, now the reason for that, like I said, if I'm going back and forth between a log and an exponential, if this is the log equation, then the exponential equation from whence it came is going to be a raised to the y equals x. And we got those same restrictions on a. A has to be greater than 0, and a can't be equal to 1. So can we make sense of that? Of why those two restrictions are there on a based on what we've studied about exponentials up to this point? Consider each case individually. A greater than 0. What if a wasn't greater than 0? What if a was something negative? Okay. What would happen if a was negative here? Would it, when we graphed it, would it still make that nice exponential curve going up? What would happen to it? It would keep going back and forth, right? Positive, negative, positive, negative, because as soon as you keep raising that base to a higher and higher integer, it's going to flip-flop back and forth. And so it doesn't really follow that exponential pattern anymore, okay? What if a was 0 itself? What's bad with that? It just, right, it just stays 0 all the time, right? 0 to some power, it's still just 0. So it'd just make a flat line. That's not exponential, right? And what if a was equal to 1? What's the problem with that? It'd just be 1, right? 1 to any power is still 1. So that wouldn't be exponential either, just be this nice flat line. Okay? So we got to have those restrictions on the exponential, and because the log comes from that exponential, we have to keep those same rules for a. Can't be, or yeah, has to be greater than 0, can't be equal to 1. Okay? So, it's new. Okay, some special logs that we use, that these should be somewhat familiar. The natural log, and this is simply where the base is equal to e. That's one that we'll use quite often. And we also have what's called a common log, which just looks like this with no base, log x. And in that case, the base a is equal to 10. So, like I said, you've seen those before, but just to do a little refresh here for you. Here. These are going to be useful for you. Not only right now just working with logs, but later on when we start working with derivatives and integrals and really get into the calculus, one thing we're going to want to do is to take an equation we're working with, like if we're trying to find a derivative or integral of some function we're looking at, more often than not we're going to want to simplify that thing or change it to something else that will allow us to do those calculations. Because sometimes in one form you can't do it, but as soon as you switch it, write it in a different form, then you can do whatever it is you need to do. So these problems we're going to end up using quite a bit with that. So first one is a to the log base a of x. If you raise something to a log, okay, you're doing the exponential of a log. And those are two opposite things. They cancel out. So what is this equal to? Just x, right? Okay, so that's showing you that those two operations are canceling each other off. It would just be the x then. And what about if you have log base a of a to the x? So you're taking the log of an exponential now. What about that? That one also comes out to just x. Those two operations cancel each other out. Works same way if you're doing natural logs. I mean, they're both the exact same. It's using a base of e, but it's good to kind of see it. E to the natural log x is also just x. It's the same rule. And the natural log of e to the x is also just x. Works the same way. Okay? So those are some first for the exponential and the log. Okay, because they're inverse operations that are going on there. Okay, some other logs that you guys studied quite a bit in Algebra 2 as well as pre-calc that it's worth noting. Like I said, I'm not going to delve too deep into these, but they should look familiar. First one is the product rule. So with the product rule, so if I have the log base A is y, anybody remember what we can do with that then? Mm-hmm. Kind of break it apart into an addition problem. Yep, that's the product rule. And it goes both ways, obviously. So if you have two logs that are added together and you would like to bring them together into one, which usually will be, you can do that. If you understand the product rule, the quotient rule is pretty straightforward then as well. So if you have the log base A of x over y, what's the only thing that changes? Yeah, it's just a subtraction then. And then the one we're probably going to use the most, the power rule. And this one was log base A x to the y. Anybody remember what we can do with that? If we have a log of something raised to a power? Mm-hmm. We can bring the power down and multiply. All right, so let's see. So if we can use these properties at all to help us solve some problems, that's going to be kind of our last goal here with this stuff is, can we solve equations involving exponentials and logs and that sort of thing using some of these properties out. So let's say we've got so how about 2 times 5 to the x plus 2 equals 20? So if I want to solve this for x, first thing I'm going to need to do is divide by the 2. So we've got 5 to the x plus 2 equals 20. Now there's two different approaches to this. 10. Oh, right, 10. Thank you. Mr. Herrick hasn't had his coffee yet. Okay, that's 10. So next thing we need to do, like I said, there's two approaches to it. You can either think about applying a log to either side of the equation, or you can think about taking this equation and rewriting it as a single log equation. Okay? So I'll show you both ways. Whichever you like best, go for it. I'll tell you which one's my favorite. So if you apply a log, you'll need to make sure you use the same base as the exponential side of your equation. Get that. Log base 5 of 5 to the x plus 2 equals log base 5 of 10. I put a log base 5 on both sides. Okay? Using our, let's what's going to happen right here on this side? We'll just end up with x plus 2, right? One of those inverse properties or whatever. It's going to cancel out. Exactly. I used a 5 here because this was a 5, and I knew that would cancel it out then. Okay, but I got to make sure I keep my log base 5 of 10 over there. Okay, and then solving for x, x is equal to log base 5 of 10, that quantity, whatever it is, minus 2. So if I was looking for an exact answer, there you go. You can just leave it like that. More often than not, we're going to want a decimal for this thing. So we're going to have to actually evaluate it. Now, to evaluate this log here, we're going to have to use the change of base formula. See if you guys remember this. Because your calculator doesn't have, well, some of the new ones do, but most of the old ones won't allow you to do a base of anything other than 10 or e. So the change of base formula allows us to turn this into a division problem. So it looks like that, okay? And that should be somewhat familiar to you at this point. So in any event, log 10 divided by log 5 is 1.43. And then if I subtract 2 from that, x is negative 0.57. Okay, so that's using the applying a log type process there, okay? So if I went the other way with it, which is just turning an exponential equation into a log equation and kind of working from there, that's another way of looking at it. Students in the past, I don't really like this way because they have a hard time remembering the conversion from one to the other. It's an important thing to know, but if you can get around it by doing this other process over here. But if you can remember it, I think it has a little less work involved. So it would become a log base 5 and equals x plus 2. You can immediately go to that step. The base of the exponential is the base of the log. What the exponential is equal to becomes part of the log, and then whatever the exponent was is what the log is equal to. So if you can keep all of that straight, you can skip a step and jump right to here. And from there, it's really the same process. So then x equals log base 10 minus 2, and etc., just like we did on the other one. X is equal to negative 0.57. All right, so just another way to kind of look at it there. So that's those kind of equations. There's some other exponential equations that will involve some logs that we're going to solve. And I'll do one of them with you here. Get a little bit tricky. We did some in pre-calc, and they're always the one that inevitably I would have questions on the next day after we did the assignment, because people were still like, I don't like this. So we'll do one together. Let's say 2 to the x plus 2 to the negative x equals 5. Anybody remember these? Yeah, maybe. We're going to use the quadratic formula to help us. Yeah, you probably. But, okay, so here's the strategy. You multiply the entire equation by the exponential that you see embedded in there. And be careful, because one of these is a positive, these is a negative x, but we do it with the positive x. Okay? The reason for that is negative exponents are just messy. They create fractions, and I don't want to mess with that. So I got an equation. I am free to multiply that by whatever I want, as long as I do both sides the same thing. I'm just going to multiply by a 2 to the x, and it's going to take care of that negative x for me. Okay, so let's think about distributing this. 2 to the x times 2 to the x. What does that get me? Well, I have the same base, and I'm multiplying. What do I do with the exponents? Add them. So it's 2 to the 2x. Same thing here. 2 to the negative x, 2 to the x. If I add these exponents, what do I get? 2 to the 0, right? Negative x plus x is 0. And then be careful here, it is not 10 to the x. Very common mistake. Okay, this is inside the x, or this is the base of the exponential. This 5 is not. So really, it is just this, 5 times 2 to the x. Okay, so what's 2 to the 0? 1. Anything to the 0 power is 1. So I rearrange a little bit here and turn it into a 1. Everybody with me so far here? What I just did there? Just pushed everything to one side, turned that 2 to the 0 into a 1. Okay. Now rewrite it another way here. That'll hopefully clarify what's going on next. Anybody start to see now why I need to use the quadratic formula? So what I've done is I've created a quadratic equation that is not quadratic in x, it is quadratic in 2 to the x. Even though it's got that little exponential mixed in there, it don't matter. Okay, still quadratic. Okay, so when I do my quadratic formula, I have to make sure that it is 2 to the x equals whatever it is, rather than just x equals whatever it is. Okay, so we still have a b and a c for this that we can use in that quadratic formula. See if we can identify them really quick. What's a? 1. What's b? Negative 5. And c? 1. Okay, so 2 to the x equals negative b, 5, plus or minus the square root of b squared, 25, minus 4ac, all over 2a. But notice, like I said, it's 2 to the x equals all that garbage, rather than just x equals. Okay, because we have a quadratic with 2 to the x in there instead. We're not about that until we can get an answer from this, though. Okay, so 2 to the x equals, so 25 minus 4, the square root of 21. So this is 5 plus or minus the square root of 21 divided by 2. So let's see what those two answers are. So 5 plus the square root of 21 divided by 2. So I get 2 to the x equals 4.791. And then if I use the minus, 5 minus the square root of 21 divided by 2, 0.209. So I have two little exponential problems now to solve. And then I'm done. So what do I got to do then? Kind of like the last problem we just did, right? Got two choices. You can either apply a log to either side, or you can just switch them into exponential equations. Or switch them into log equations and solve it. So I'm just going to switch these both into log equations over here. So log base 2 of 4.791 is equal to x, which is log of 4.791 divided by log of 2.26. And then the other one that I had, log base 2 of 0.209. So if I do log of 0.209 divided by log 2, negative 2.25. Or I guess 2.26. So those would be your two answers then for that one. Okay? So there will be one like that in your homework. I believe it uses E instead of 2, but it's the same general idea. Okay? All right. You guys get going on some work here. I know we're a little close on time.